Well, welcome back, guys, and I do hope during this challenging time with schools being closed, you and your family are keeping well. So what we're going to do today is start a new topic. What we're going to look at is electric fields. So, electric fields, they have lots of similarities, in fact, mathematically, to gravitational fields. So, if you know the work that we've done in previous videos on gravitational fields, you should have a fairly good start on what electric fields are and how they behave. So, the first thing we're going to look at is what a field actually is. And you should remind yourself that a field is a specific thing in physics, and I'll take the time to actually write it all out. It's a place in space where... Now, we have to stop here for a second, because which field are we talking about? Well, if it's the gravitational field, it's a place in space where masses feel forces. But we're looking at the electric field, so it's a place in space where charges feel forces. Now, the reason we need the idea of a field, of course, is because when you have, for example, a positive and a negative charge, they will attract, and a positive and positive charge will repel, not unlike magnetism, and there are lots of connections there too. And between the two things, between the two objects that are charged, or between the two charges, you can't see anything happening, because it's a non-contact field. Or more importantly, it's a non-contact force that you see. So we need some kind of mathematical model to kind of indicate what's happening between the two to try and explain why they feel forces, and it's the field that we use to do that. So what we're going to look at now is how we can create an electric field and how we can detect it's there. So firstly, let's look at how we can create an electric field. And I purposefully put this jumper on today because it's quite successful at creating electric fields. You know, when you pull a jumper off in the evening, you hear that crackling sound. There are little tiny sparks flying inside it, because during the day, with its rubbing, it's created an electric field. So let's look now at a number of ways that we can do that. Creating an electric field. So the one I mentioned firstly there, to do with the jumper, was when you rub insulators together. So you might have done experiments when you were much younger where you sort of rubbed bits of plastic and little bits of paper stuck to it, or you could bend water in a tap, etc. Electrostatic effects. That was creating electric fields by rubbing. And you needed to get charge on the object, so it needed to hold its charge, so you had to rub an insulator. Now, you might have been under the pylons, the national grid, and heard that sort of fizzing, crackling sound. My horse used to be in a field with the high voltage power cables going over the top, and there was this constant fizzing sound because the pylon itself was earthed, and the cables were at a very high voltage, maybe 440 kilovolts. So between them, you've got a high potential difference, a high voltage, and that creates an electric field. So we can create an electric field between two high voltage points. Obviously, what you understand by that is a high voltage potential difference between those points. And a really good example of that, and one of the biggest that you will ever see, of course, obviously you might have seen Tesla, the photographs of him playing with his Tesla coils, or you might have seen the large Van de Graaff generators. But if we scale up the rubbing effect, the effect you get in thunderstorms. Now, what you've got there is a very large potential difference forming across the cloud and also across the cloud and the ground, and that creates a very strong electric field. And that electric field, in the end, will cause the air to ionize, and you'll get a strike of lightning coming down. So let's quickly look at how we can actually create an electric field with a sort of diagram, okay? And then how we can detect it. So detecting electric fields. Now, obviously, there will be an electric field between two objects at a different voltage. In other words, if there's a potential difference across them. But I was thinking more in terms of taking an object and charging it up. So the sort of thing we always do in physics, and it goes back a very long way, is we imagine an insulated conductor. So here's the conductor hanging off an insulated sort of piece of nylon or something, piece of silk thread back in the day. Okay, and we connect that to a high positive voltage and therefore remove electrons. And interestingly enough, if it is a conductor, the electrons will be removed from the surface and will leave a positive charge over the object that's evenly spread out. Okay, there'll be no field inside that hollow conductor, but there will be an electric field around here. Now, how can I prove that to you? Well, one way of thinking about it is if you were to touch this, there'd be a little spark. Okay, I suppose this stores charge, it has capacitance. But what I wanted to show you was around here is this invisible force field. Now, the way we can detect that, a very simple way, and this is a pretty lame demonstration, and it's very hard to show, is I've got a very thin piece of gold leaf here. Okay, it's so thin that I broke it before I actually brought it up to the camera earlier. Okay, and if I was to make that charged up, in other words, I touch it onto here and make this positive, you're aware that this is positive, that'll be positive, and therefore this will feel a force of repulsion. It's flicking around at the moment, not because I'm wiggling my hand, but just the air in the room and my voice is enough to make this gold foil flick from side to side. So I'll put that down safely. Okay, and what we'll do is we'll imagine we've got our insulating holder here. There it is. And our piece of gold foil on it, that's positive. And the piece of gold foil will repel because it's positive. Okay. So it will move out of the way. Some of you might remember the gold leaf electroscope, which is sort of a similar idea. Now, what I wanted to mention here was, what happens if we move this detecting object that's finding this force field further away? So I'll now move it over here. Well, I'm sure you're all aware that if we move it further away, the field from here will get weaker and weaker. So the gold leaf will retain its positive charge, and that charge will be the same. But we've moved it further away so it doesn't feel such a strong force. Okay, it won't hang vertically because it still feels the effect of the field. But what's important is from the center of this charged sphere, we've moved away two different distances. Okay, and because it's radial, because we've come from the center and we've moved out along a radius, we're going to label this distance in all our diagrams later on R. Now you'll notice that I picked this example specifically because this feels a force due to the invisible electric field here. Charged objects feel a force in electric fields. The field gets weaker as we go away. Okay, we check its presence with a test charge, and here's where it gets a bit complicated. What about the field of this one? Okay, so we can't make the charge on the testing object too large, otherwise it will distort the field due to this one. Okay, so we put a very small amount of charge on there. And you'll notice, even though it's a bit like gravity, this, okay, you'll notice here that plus and plus repel. So you can remember that in some A-level questions, that electric fields are both attractive between plus and minus and repulsive between similar charges. And that is not the case with gravity, of course. Gravity is always attractive between masses. So now let's look at electric field strength. How strong is the electric field at any specific point in space? Now, again, gravity, you need a good understanding of gravitational fields to help you with this, or at least if you understand gravitational fields, well, it will help you. So, the electric field strength works in a similar sort of way mathematically. If you remember, the gravitational field strength was the force per unit mass, and the electric field strength, E, is the force per unit charge. Okay. Now the important thing is it is a vector, it has a direction, okay, so the electric field, E, is a vector quantity. So to get its vector nature, force is a vector quantity as well. Okay, so it's important you understand that, and then you have to decide, okay, which way is the force? Is it between repelling things or is it between attracting things? Okay, so remember, this is always done in terms of a positive charge. Now, clearly, the electric field, there will be an electric field when you're looking at negative charges, but you must remember that the direction of force is always, the direction of field is always the way a positive charge would move. Do you remember in my previous slide we talked about the test charge? Okay, so even if you're looking at negative charges, you would imagine what would happen if you put a positive charge in there, which way would it move? And its units, well, I guess its units are fairly obvious. The units, you can write them in a number of ways, okay, but the units of E will be newtons per coulomb. Newtons per coulomb. Well, let's do this properly. Newtons, coulombs to the -1. Okay, and I'm just going to indicate on here that the electric field, if I say this, you'll remember to put arrows on it, is a vector quantity. You never seem to have problems putting arrows on forces, but people forget when they're asked to draw on a field, they forget to put on the arrows to show which way the field vector points. Okay, my final bit on this one is letters. Okay, we can get in a terrible tangle with particularly the C. Okay, in this case it's a unit, so it's coulombs. In formulae with electric fields, it's C for capacitance, and you can sort of see the confusions we're going to get. E gets confused with lots and lots of things as well. Okay, so you have to think about which area you're in. You have to think about the context of the question and then go, yep, I know what all those letters stand for. So let's now do a quick example, and I think this will bring all the ideas that we've done so far together. Okay, so quick example. Now it'll take me a while to put this one together, but I'd like to write it down in front of you. Okay, so we want to calculate an electric field strength. Okay, and what we're going to imagine is, I noticed this because I play with records a lot, old vinyl records. You rub them clean and little dust particles stick to them straight away, and you clean it again and the dust sticks again. Okay, dust can build up a charge via a number of methods, but what we're going to imagine is that we've actually got some dust or a small particle and it is already charged. Okay, so imagine a small dust particle. Yep. And this dust particle has charge on it, and it has 1,250 extra electrons on it. Okay. So it was neutral, and the number of protons and electrons were equal, but for some reason it's picked up some extra electrons, so it's now negatively charged. Okay. And it gets put in an electric field. So there's a place in space where charges feel a force. And I'll give you a value, I'm sort of making the numbers up, a value of what force it feels, and then we'll calculate what the electric field strength is. So it feels a force. And this force is going to be very small, 3 times 10 to the minus 12 newtons. Okay. You might want to think what's 10 to the minus 12 called. Okay, if 10 to the minus 9 is called nano, what's 10 to the minus 12? Okay, because it's another 3 orders of magnitude smaller. And we're going to ask ourselves, what is the strength of the electric field? So what value of electric field is it in? Okay, so we've got our equation for the strength of the electric field. So we've got the force, we know the force, and we need to know the charge on the dust particle. Okay, so we've got 1,250 electrons, 1.6 times 10 to the minus 19 coulombs for the electron. Now I haven't put the minus in there because we're not going to draw a diagram, so we're not actually going to put the vector arrow on the electric field. Okay, but if I just work out the charge on the object, it's 2 times 10 to the minus 16 coulombs of charge on it. Okay, now you might think, well, hang on, that's a positive charge. Well, all right. This is the charge on a proton. E is the charge on a proton. So let's now do it properly. That's the charge on an electron. So it will be a negative charge by definition. And I guess I should put that in brackets now just to make it a bit clearer. Okay. So we've now got the charge on our little dust particle. We know that the electric field strength, E, is the force per unit charge, okay, F over Q. So the electric field that it's in will be the force it feels, 3 times 10 to the minus 12 newtons, divided by 2 times 10 to the minus 16 coulombs. Okay. I'll put the minus in there just for the sake of it. You'll see why that's interesting in a minute. And if you work that out, okay, this is a small number, that's an even smaller number, so this has to be a larger number. There's a minus there, 1500 newtons per coulomb. Now, you don't really need the minus here, but the point I'm making is it kind of indicates the direction the field would go. So our dust particle is going to go in one direction because it's negative, but remember that this minus here represents the dust particle's direction is the opposite direction to the arrow you'd put on the electric field. Okay, and just get a feel for what that means. It means that if you had a coulomb of charge, you don't, yep, you have a much lower amount of charge. Okay, but if you had a coulomb of charge, it would feel 1,500 newtons. Okay, so now let's look at some electric field shapes. So can we draw the shapes of electric fields, remembering to put the correct direction on them? Well, the place to start, of course, and the one you're most familiar with, I hope, is the parallel plate capacitor. So our first example will be 2 parallel metal plates. There's the first one, and there's the second one. And here are the connections. And if we leave that as it is, there's no electric field in here. There's a gravitational field. It's really important you understand that. There is a gravitational field at 90 degrees to the electric field. That'll be interesting when we do sort of equations of motion on this sort of thing, when we combine fields. But if it's uncharged, there's no electric field. So let's charge it up. And if you remember, what you do is you steal electrons from one plate and you feed them onto, or at least you feed the charge onto the other plate. I'm kind of not suggesting it's exactly the same electrons, but it's equal and opposite charge. So, of course, if you look at that, it's neutral overall, but there's a separation of charge, and the electric field is defined as the direction a positive charge would move. So, when we draw this, we have to be a little bit careful. Okay, a positive charge would move to the left, to the left. Just keep drawing. Do you notice, I'll talk whilst drawing, that these lines are all the same distance apart from at the edges, the fringing field. Okay, it's not quite finished. I hope you feel that that's not quite finished. So the electric field in there is uniform, and it is the same strength at every point. Okay, I'll just say that again. It's the same strength here as it is here, as it is there. Very quickly, okay, a positive charge here will be pushed hard by the positive and not pulled very hard by the negative. And as we get close to the negative, it will be pulled harder by the negative and pushed less hard by the positive. So it balances out. So the field strength in the gap is uniform, and it is the direction a positive charge would move. And then we have this complication of the fringing field on the outside. And even some A-level questions, some university questions talk about infinitely large parallel plates. So you don't have to worry too much about the complexity of the field fringing on the outside. So what we'll do now is say, okay, well, that's easy enough. Those are parallel plates. What does the electric field look like around a spherical hollow conductor? So now let's do the spherical conductor, closed conductor. I'll draw it over here. And whilst I'm drawing this, usual story, think gravitational fields. Spot the similarity. Oh, look at that. That's not bad, is it? Okay. So let's remove some electrons from this. You might wonder why I'm going for positive every time, but there's kind of a good reason for that, but it doesn't matter. Now, do you remember what I said? There will be no field inside the closed conductor. Okay, and those of you who know about Faraday cages might have a feel for what I'm talking about there. The next thing is, if you think about electrons bunching up in one place, they'll scoot out of the way and spread evenly. So they'll also be removed evenly. In other words, if we remove a few electrons from the bottom here, because this is a conductor, okay, the electrons that are at the top will be too close together and they'll spread evenly over the object, leaving it positively charged. Okay, in other words, an even amount of charge. And textbooks don't really make this point, but if it's an even amount of charge, then the field lines that sort of enter here are going to be the same number as here and here, if you see what I mean. Okay, not sure I've explained that very well. So let's draw the electric field on. This comes up a little bit in exams. Draw 4, draw 8 field lines on the object. Okay, so it's a radial field. So there are 2. There are another 2. And why not? So that one and that one. You'll notice I'm using a ruler because you really should do this well in an exam. And then finally, I've lost a mark, obviously, because the direction of the field is the direction a positive charge would move. So I need to show the vector nature of the field. And it's really important you understand that it is a vector field, not so much at A-level, but more at uni. But if I start to put another charge in here, the overall field we get is the sum of the two fields' magnitudes, taking into account their direction. So it is the vector sum, which can get a little bit tricky. This one has a particular name. It's coming out along the radiuses of the object, so this is a radial field. And I did it to draw similarities with the gravitational field, but to make the point that the electric field can go away from the object as well as towards it if it was negative. Okay, so whenever you draw that, be very careful to draw the field lines with a ruler and to draw the direction. And finally, remember this is three-dimensional. Okay, so we've got field lines coming out towards us, spreading out as well. So they're spreading out in this direction, and they're also spreading out in this direction. So that might give you some idea as to the mathematics behind the field on this shape. So just for fun, I'd like to do two more. I'd like to do the Thundercloud example. Now, this is going to be a little bit of a tricky fella to draw, but it's important that you understand how the field lines sort of form in this situation. So here's the ground, and we'll assume the ground to be earthed. The earth itself can kind of mop up free electrons quite easily. And then we'll draw a tall building. I usually go for a church or something like that because it has a spire. And it's probably got a lightning conductor on top. And we won't get into the detail of that. Okay, so the whole of this object is earthed as well. Now, granted, a church is made of sort of bricks and stone and stuff, but there's enough conduction going on there for electrons not to build up on it and for it to remain charged for the existence of the building. I'll put a lightning conductor on here. We won't worry what shape we make that, whether we make it a sort of trident or spiky or a flat disc on top. We'll just draw it like that to begin with. And what I'll do is draw my wonderful cumulonimbus up here. Doesn't look anything like a cumulonimbus cloud, but you get the idea. Okay. And again, the detail of how thunderstorms work is really complicated, and I think scientists don't fully agree yet. But what we'll suggest is that the cloud has become charged up by movement, by currents inside the cloud, particularly of ice particles, which are very dry, rubbing against each other. And we'll suggest that the charge separation in the cloud is something like this. Okay, and I've done it this way round because this is one of the ways it's suggested that the charge separates on cumulonimbus clouds. It's a bit more complex than that. But I've put the negative charge at the bottom of the cloud with good reason. Well, you can see there's a field inside the cloud, but we won't worry about that one. But what about compared to the object down here? Well, straight out of the cloud, there we go. Here's another straight line. Here's another straight field line. Okay. Now, before we go any further, we better draw the direction. Okay. There's two clever things that happen here. One of them is this is at 0 and this is minus. So this is 0 and that's a lower voltage. So the direction a positive charge would move would be that way. Okay. But you also get another interesting effect called induced charge. I don't want you to worry about that too much. But can you imagine the electrons on the bottom of the cloud being negative, having an effect due to the field on the electrons here and repelling them into the ground? So what they'll leave behind is the protons, or more importantly, the positive charge. So the top of the building will actually charge by induction. If you were just to start my lesson now, you might go, how did those positive charges get there? Okay, this is not something to worry about too much. Now, what about here? Well, the field lines will enter and leave all surfaces at 90 degrees, so it'll come out and then up to the cloud. Okay, out and then up to the cloud. But I wanted also to show you what happens on this fine point. Out of the fine point and up to the cloud, out of the fine point and up to the cloud, and the same here. So leaving and entering all surfaces at 90 degrees. Now, I haven't done the ground as well, but what's really interesting here is the field is not totally uniform in this area. Okay. You've seen the field leaving and entering all surfaces at 90 degrees. And because this is a fine point, and they come in like that, almost coming in radially, because you can imagine it's like a little dot, a little sphere, the field here is much, much stronger than the field here, because the field lines are coming in and concentrating on that point. And that's a hint on how lightning conductors actually do their job. But all I want to say at this stage is, look at this. On a point, on a fine point, you get a very strong electric field. So finally, let's draw the diagram to show the electric field between two spheres, hollow spheres that are charged up. So there's one, and there's the other one. Okay, and what I'm going to do is I'm going to charge one positively and one negatively. So that's easy to do. Positive of a power supply, negative of a power supply. Okay, so the positive of the power supply will attract the electrons off this one and leave it positive, and they'll be forced by the power supply onto this one and make that negative. So this will be covered in minuses and this will be covered in pluses. There's a slight twist here though, that if this is covered in pluses, the electrons that are evenly spread over this will be attracted towards this one, so they'll pile up on this side. And the same will apply here, that any extra electrons that are in this area will be pushed that way, so the positives will kind of pile up here. So it's more correct to draw this diagram in this sort of way. Not sure you'll get this at A level. Okay, with a sort of excess of a slightly bigger charge density on this side and here. But for the sake of what I'm drawing, I haven't counted them, by the way. It should sort of be even, equal amounts. Okay, for the sake of the diagram, this is a sphere, hollow metal sphere, that's negatively charged, and that's one that's positively charged. Okay, and now let's draw the field lines. Well, the direction a positive charge would move, leaving and entering all surfaces at 90 degrees. Leaving and entering all surfaces at 90 degrees. Okay, here's one from far away coming in, and here's one from far away going out. Okay, and the next one will sort of do this, come round and that. I'm trying to make that gap there much bigger than this one because it's a very non-uniform field. Okay, so not a particularly easy field to draw. I'll give a go at one more line. And this one. Now, if you remember, this is a little bit like, that's not brilliant, but it'll do. It's a little bit like magnetic fields, that these continue off the page and come back. They're sort of off the bit of paper that we can draw. And I have to be careful now. I've seen this wrong in textbooks. The way a positive charge would move, yeah, it would move that way, and it would move that way. Okay, so I hope I got all the arrows the correct way. So now you can see we've done the vector sum of the two fields there, but we've done it just by drawing. It makes life a bit easier. And we've shown the field lines leaving and entering at 90 degrees, just about. Okay, and the final thing with this one is these charged metal spheres, hollow metal spheres. What we're going to do later on is we're going to back off and back off and back off and back off from them. And if we back off a very long way, they're going to appear just like dots in the distance. So later on, we can assume that these are point spheres, point charges. So you could imagine the electron or the proton being a point charge at a long distance. And then you could imagine the field lines have actually come from a point right in the middle. Okay? But it's really important that you don't draw a field inside a closed conductor. I think we need to go to university for me to explain why that is. But we've got a good diagram here of close-up, and just imagine how you would visualize that if you were a long distance away. So I do hope you found that introductory and first video lesson on electric fields useful, and you feel you've got a good understanding now of what an electric field is and how you would draw the shape of an electric field. So I'll be making another video soon, and as ever, I look forward to seeing you then.